We continue polynomial functions and how to graph them using the leading coefficient test and finding the intercepts, the X and Y intercepts, and looking at the symmetry and the number of turning points. We might need some extra points if we can't identify the function's behavior just by using, say, parts 1 through 5. So, the leading term here is x cubed, and the leading coefficient is 1. So what we have is an odd degree and a positive leading coefficient. This would imply that the function rises on the left and rises on the right as well. Keep in mind, it can make turns in the middle. So we can't simply say it's going to go like a straight line or a curvy line just going up. It could make a turn right in the middle, so we've got to be careful. So we want to find the X-intercepts. The X-intercepts are the zeros of the function. So we find them by setting the function equal to 0 and solving for x. So x cubed plus 2x squared minus x minus 2 would equal 0, which would mean I have x squared in common in the first two terms. So if I pull x squared out, when x squared comes out of x cubed, I have x. When x squared comes out of 2x squared, I have 2. The last two terms have minus 1 in common, so if I pull minus out, I have x. And minus, when it comes out of minus 2, I have x plus 2 left. These two terms, that and that, have x plus 2 in common. So if I pull x plus 2 out, from the first term, I'd have x squared left behind. And if I pull x plus 2 out from the second term, I have 1 with a negative. And x squared minus 1 is a special quadratic function, and we can write it as x plus 1 times x minus 1. So we have three factors. So factor number 1 is x plus 2, factor 2 is x plus 1, and factor 3 is x minus 1. So the factors are distinct. This would mean the roots or zeros have a multiplicity of 1. If I set the first factor equal to 0, x plus 2 equals 0, which would imply x is minus 2. If I set the second factor equal to 0, x plus 1 is equal to 0, which would imply x is equal to minus 1. And if I set the third factor equal to 0, x minus 1 is equal to 0, which would imply x is equal to 1. So the three zeros are x is equal to minus 2, x is equal to minus 1, and x is equal to 1. Those are the x-intercepts. those are the points where the function would cross the x-axis. To find the y-intercept, we simply plug in x is equal to 0. So f of 0 would equal to 0 cubed plus 2 times 0 squared minus 0 minus 2, which would give us minus 2. And that is the point where the curve would cross the y-axis at minus 2. And we would want to test for symmetry, and we have two kinds, y-axis symmetry and origin symmetry. So if f of minus x is equal to f of x, then the function is symmetric about the x-axis. So let us find f of minus x. So f of minus x would equal to negative x cubed plus 2 times negative x squared minus of minus x minus 2. And you can see that I'm putting parentheses around negative x so that I can keep track of signs properly. Negative x cubed is simply negative x times x cubed. Negative x whole squared is 2x squared. Negative times negative x is positive x and minus 2. And that doesn't look anything like f of x. So we do not have y-axis symmetry. And if f of x, f of negative x is equal to minus f of x, then we have symmetry about the origin. So if I pull a negative out of f of negative x, which is right over here, I have negative multiplied by x cubed minus 2x squared minus x plus 2. And once again, that doesn't look anything like f of x. F of x is x cubed plus 2x squared minus x minus 2, but we have x cubed minus 2x squared minus x plus 2, so we can conclude there is no symmetry about the origin. The number of turning points, since the degree is 3, the function would have at most 2 turning points. So with all these bits of information we have, let us see if we can sketch the graph. So we know that the function crosses the x-axis at negative 2, negative 1, and 1. So negative 2, negative 1, and 1. In addition, the intercept is at, the y-intercept is at negative 2. So I'm placing a dot there. What we know here is, since the function has an odd degree and the coefficient is positive, the function has to rise on the left-hand side of 0 and rise on the right-hand side. And so it has to go up again, but once it goes up, it has to make a turn to pass through 0 again. And the function would come through the y-intercept, and since it has another point to pass through here, I didn't mean to erase that, so it has to turn around and pass through that point. So that is the function that we have. Now, how did I graph this? I simply looked at the point where the function would cross the axis, which is right here at -2, right there at -1, and right there at +1. And I used the fact, since it has an odd degree and the coefficient is positive, so it rises on the left and it rises on the right. But keep in mind, just because we say it rises on the left and rises on the right doesn't mean the function will not make a turn, as it is obvious in this particular problem. Since there are 0 crossings, the function that's going up has to turn around and come back through a 0, in the sense that the function was rising up as it got closer to -2, and it could have gone up, up, and up, but we know that the function crossed 0 again, so it should have turned. So it turned at -1, and it could have kept going down, but it cannot, because there is another 0 crossing coming up, and in addition, there is a y-intercept. So the curve has to pass through the y-intercept, and it has to turn because it has to meet that 0 crossing at x is equal to 1, and then keep going up. So just by noting these 5 points, we can, or these 5 bits of information, we can sketch a graph of a polynomial function. So this example is straightforward in the sense we have the function in a factored form already. So f of x is -2 times x minus 2 squared times x plus 1. Now, there is no need to FOIL to find the leading term. So all we have to do is take the coefficient that's here, the coefficient of that term, and the coefficient of that term. So what we have is -2 times 1 times 1. And in the second term here, we have a square. So in short, it would simply become x squared. And the third term, we have x plus 1. So in short, that would become x. So the leading term would be -2x cubed. So that is the leading term. The leading coefficient is -2. So what we have here is an odd degree with negative leading coefficient, which would imply that the function falls on the left and falls on the right. Once again, just like we'd seen in the previous problem, this does not imply that the function cannot make turns between or around the origin or somewhere in the domain of the function. It could turn like it did in the previous problem. So the second step is to find the x-intercepts. The x-intercepts are once again the zeros of the function. So we set f of x equals 0 and solve for x. So the polynomial here is nicely factored. So if we divide by -2, we simply have x minus 2 squared times x plus 1 equals 0. We have x minus 2 times x minus 2 times x plus 1 equals 0. Those two factors are identical. This would mean that x minus 2 equals 0 would yield us x is equal to 2, but it repeats twice. Therefore, the multiplicity of x equals 2 is 2, because it repeats itself twice. And next we have x plus 1. If we set x plus 1 equals 0, we would have x is equal to minus 1. To get the y-intercept, we simply plug in 0 for the function. So -2, 0 minus 2 squared, and 0 plus 1, and -2, -2 squared times 1, -2 times 4 times 1, which would give us -8. Checking for symmetry. So if f of x, or excuse me, if f of minus x is equal to f of x, then we have y-axis symmetry. So let us find f of minus x, which in this case would be -2, -x minus 2 squared, -x plus 1, which would give us -2. There is a negative in common in that term, so if I pull that out of the square, I'll have -1 squared times x plus 2 times -x plus 1, which would give us -2 times x plus 2 times 1 minus x. And clearly that doesn't look anything like f of x. So f of minus x is not equal to f of x, which would indicate that there is no y-axis symmetry. Now, is f of minus x equal to the negative of f of x? If it is the case, then we have symmetry about the origin. So negative of the function f of x, which is -2 times x minus 2 squared times x minus 1. So that is negative f of x. And negative times -2 is positive 2. So 2 times x minus 2 squared times x minus 1. And that doesn't look anything like the given function. The given function has a -2 in the front, but here we have a +2, so negative f of x is not equal to f of x, which would imply no symmetry about the origin. So let's try and graph this, but before we do that, the turning points, since the degree is 3, the number of turning points at most would be 2, which is n-1. So let's go back here. We know that the function has to fall on the left and folds on the right, and we have found that there is a 0 at 2, so let's mark that point. There is a 0 crossing here, and there is a 0 crossing at -1. And there is 1 at 8. Or is it -8? I believe it's -8. The Y-intercept is at -8. So it's right over there. So we know that the function is falling down on the left-hand side, so it's coming down of that sort. And it has to keep on going down, so it goes down. And it has to turn somewhere here, not necessarily at 8, but it has to turn at, at -8. It has to turn because there is a 0 crossing up there, so it is going to go up. But we can't do that because the function has to be falling on the left-hand side and the right-hand side. So we can't simply draw that. That would be incorrect. So because it has to fall on the right-hand side. In other words, it has to do that, which would imply the function is going up and it's turning somewhere in there and coming down. So that would be the shape of the function. So we have to put a few things together to come up with the shape of the curve. Of course, this is not a perfect sketch because I'm drawing it with my hand, but if you can't recognize it right away, you can also plug in extra points, which is what part 6 here is talking about. Find extra points if needed, in the sense, for instance, we could plug in one, for instance, and when we plug in 1, we missed something. When we plug in 1, we see something interesting, so which is -2 times 1 minus 2 squared times 1 plus 1. So which would give us -2 times -1 squared times 2, which ends up being -4. So that point up there, right there, cannot be correct. So which is why sometimes we need extra points. In addition, there is another property about multiplicity that one should know. Even though the degree of the polynomial is 3, the multiplicity tells us a lot of things. If we have an even multiplicity, then at that particular point, the function has to touch and turn. So finding this right here would help us find mistakes like we did earlier, which is going through the x-axis and making a turn. For one, we can't do that because we went through the x-axis more than 2 times. So now, I hope you understood how we can easily make mistakes in a problem like this. So if we took care, we will see that at 1 we have -4, and then recognize that this root has even multiplicity, which would imply the function has to touch and turn. So we will go up that way, touch and turn. So let's see if we did the other points correctly, at least approximately correctly. So if we plug in 4, what would we get for f of 4? F of 4 is -2 times 4 minus 2 squared times (4 plus 1), which is -2 times 2 squared times 5, which is -40. So even though we drew it this way, we can see that the curve is dropping down faster than we realize. So perhaps it's going so it's touching -8 on the y-axis, making a turn, and takes a steep dive down and hits -40 when x is equal to 4. The thing that we have to understand is that here we can reassure ourselves that the function is in fact going down on this side, because when we plug in 4 we get -40, and if we plug in -4 we would get I'll write it over here, this is an extra point, so f of -4 would be -2 times -4 -2 squared, -4 plus 1, which is -2, -6 squared times -3, which would be -2 times -3 is +6, -6 squared is 36, you get 216, and the function climbs rapidly fast and heads over toward 216. So things to note: the leading coefficient test tells us if the function is going to rise on both sides. or rise on one side and fall on the other, or fall on both sides. So we recognize the rising and falling part by looking at the leading term. The x-intercepts tell us where the function would cross 0, and even if we made a mistake when we draw the curve, we can pick an extra point like I did to verify your answer and rectify errors. And the symmetry here tells us if the graph is symmetric or not. Clearly, the way we drew it, there is no symmetry about the origin, there is no symmetry about the y-axis. So everything falls in place and we have our curve. So I am going to complete this one also, but I would want you to try this on your own before you watch the rest of this video. So what we have here is f of x equals negative x raised 4 plus 4x squared. And the degree is 4, which is even. The leading term is negative x raised 4. The leading coefficient is negative 1. So what we have here is an even degree with a negative coefficient, which would imply the function rises on the left and falls on the right. So x-intercepts are points where the function crosses the x-axis. So they are simply the zeros of the function. So we set f of x equals 0 and solve for x. So negative x raised 4 plus 4x squared would equal 0, which would imply I have an x squared in common. More precisely speaking, I have a negative x squared in common, which would leave us with x squared in the first term. And if negative x squared comes out of the second term, we have negative 4 equals 0. I can multiply by negative 1 on both sides, which would give me x squared times x squared minus 4 equals 0, which is the same as x minus 0 squared times x plus 2 times x minus 2. Which is x minus 0 times x minus 0 times x plus 2 times x minus 2 equals 0. And we need to have 4 factors because this is a 4th degree polynomial. A 3rd degree polynomial has 3 roots and 3 zeros. A 4th degree polynomial has 4 roots, 4 zeros, 4 factors, and so which is why I'm writing it this way, so that we have factor 1, factor 2, factor 3, factor 4. But the first 2 factors are identical, so this would imply x minus 0 would equal 0, which would imply x is equal to 0 with multiplicity 2. And mind you, that is even. And the next factor, x plus 2 equals 0, which would imply x is equal to minus 2. And the next one, x minus 2 is equal to 0, which would imply x is equal to 2. To find the y-intercept, so the zeros are x equals minus 2, x equals 2, and x equals 0, which has a multiplicity of 2. To find the y-intercept, we simply plug in 0 for x in the function. So negative 0 raised 4 plus 4 times 0 squared, which gives us 0. So the point where it crosses the y-axis is at 0. Notice carefully that the y-intercept is 0 and the x-intercept, one of them, is also 0. In other words, the function is going through the origin. That is a giveaway. Now, if f of minus x is equal to f of x, that would imply y-axis symmetry. And let's see if we get that. So f of minus x is equal to negative x raised 4 plus 4 times negative x squared. So negative x raised to the power of 4 would give us positive x raised 4, and negative x raised to the power of 2 is positive x squared, and that equals f of x. So what we have here is y-axis symmetry. In a similar manner, if f of negative x is equal to negative f of x, then that would imply origin symmetry, or symmetric about the origin. Well, we already know from above that f of minus x is equal to f of x. If that is the case, f of minus x cannot equal to negative f of x. It just cannot be true. So, this is not possible, because we already suggested that f of minus x is equal to f of x. So how could we say that f of minus x is also equal to negative f of x? It just can't be true. So we can conclude that the function is not symmetric about the origin. And the number of turning points mind you, it's at most it's going to be n minus 1, which, sorry, 4 minus 1, 3. So we say at most because we could have fewer than 3 turning points. Let's see if we can draw this curve out. What we know here is the x-intercepts are at 0, the y-intercept is also at 0, and the other one is at 2 and negative 2. And what we know about this function is that the function has to rise so it rises on the left and it falls on the right. So we can draw a curve because it has to go through, and it has to pass through and it has to come back. It has to make a turn because it's crossing the x-axis one more time, so it must have made a turn somewhere over there. So we pass the zero crossing and make a turn, and it is falling on the right hand side, so it has to go down, but there is a zero crossing over there, so it has to turn back up. And you may say, oh, well, that seems to be right because, we have the curve, it has to go this way. But if you notice, we said that the function has to rise on the left-hand side and fall on the right-hand side. But it doesn't look like that in its current state. So something is off. So let's see what we can do. So what I'm trying to do here is I'm trying to sketch this curve without using extra points. But if you want to, you can use additional points to come up with the sketch. I'm trying to go with these bits of information, such as the leading term, the leading coefficient, multiplicity. I'm using those to come up with the curve. So it crossed there, but what we know is at 0, which is right here, x equals 0 has an even multiplicity, which would imply things should touch and turn. So the curve must have gone up, made a turn, touched again, went back up, and it has to make a turn again, so it turns and comes down. So if you look at the curve now, it satisfies all our conditions compared to what we were doing a few minutes ago. If we check the graph now, the graph is symmetric about the y-axis. We established that. The graph is rising on the left-hand side, falling on the right-hand side, which is our first pointer. And multiplicity here at x is equal to 0 helps us how to turn and so forth. And as I said, you can plug in other values to determine what those 2 points are going to be. When x is -1 and when x is 1, you should get 2. Let's just see if we get 2. So f of 1 is negative 1 raised 4 plus 4 times 1 squared, which is actually 3. Are we at 3? No. So using the extra points could help us finesse the details and make things better. So touch and turn, same thing happens, and touch and turn and go down. So if you want extra details, it is always better to get those extra set of ordered pairs, but to get a basic understanding of the shape, all we have to know is the 5 bits of information that we did in this problem and the problems before it. So before we finish, I'll just show you that f of minus 1 would also be 3, because we already know that f of minus x should equal f of x because of symmetry. So minus of minus 1 raised 4 plus 4 times minus 1 squared. So minus 1 raised 4 is 1. 4 times negative 1 squared is 4 times 1. 4 minus 1 is 3. And that value are one and the same.